Section 4-2, Flow Patterns and Flow Visualization. While quantitative study of fluid dynamics requires advanced mathematics, much can be learned from flow visualization, the visual examination of flow field features. Flow visualization is useful not only in physical experiments, Figure 4-15, spinning baseball, the late F.N. M. Brown devoted many years to developing and using smoke visualization in wind tunnels at the University of Notre Dame. Here the flow speed is about 77 feet per second and the ball is rotated at 630 rotations per minute. But in numerical solutions as well, computational fluid dynamics. In fact, the very first thing an engineer using CFD does after obtaining a numerical solution is simulate some form of flow visualization so that he or she can see the whole picture rather than merely a list of numbers and quantitative data. Why? Because the human mind is designed to rapidly process an incredible amount of visual information. As they say, a picture is worth 1,000 words. There are many types of flow patterns that can be visualized, both physically, experimentally, and/or computationally. Streamlines and stream tubes. A streamline is a curve that is everywhere tangent to the instantaneous local velocity vector. Streamlines are useful as indicators of the instantaneous direction of fluid motion through the flow field. For example, regions of recirculating flow and separation of a fluid off of a solid wall are easily identified by the streamline pattern. Streamlines cannot be directly observed experimentally except in steady flow fields, in which they are coincident with path lines and streak lines to be discussed next. Mathematically, however, we can write a simple expression for a streamline based on its definition. Consider an infinitesimal arc length, dr, equal to dxi plus dyj hat plus dzk along a streamline. Dr must be parallel to the local velocity vector equal to ui vector plus vj vector plus wk vector, by definition of the streamline. By simple geometric arguments using similar triangles, we know the components of the streamline vector must be proportional to those of the velocity vector, Figure 4-16. For two-dimensional flow in the xy plane, arc length dr vector is equal to dx, dy along a streamline is everywhere tangent to the local instantaneous velocity vector equal to u, v. For a known velocity field, we integrate equation 4-15 to obtain equations for the streamlines. In two dimensions, x and y, or u and v, the following differential equation is obtained. Streamline in the xy plane is dy over dx along a streamline, which is equal to v over u. Equation 4-16. In some simple cases, equation 4-16 may be solved analytically. In the general case, it must be solved numerically. In either case, an arbitrary constant of integration appears. Each chosen value of the constant represents a different streamline. The family of curves that satisfies equation 4-16 therefore represents streamlines of the flow field. Example 4-4, streamlines in the xy plane, an analytical solution. For steady incompressible two-dimensional velocity field of example 4-1, plot several streamlines in the right half of the flow, where x is greater than 0, and compare to the velocity vectors plotted in figure 4-4. Solution. An analytical expression for the streamlines is to be generated and plotted in the upper right quadrant. The flow is steady and incompressible. The flow is two-dimensional, implying no z component of velocity and no variation of u or v with z. Analysis. Equation 4-16 is applicable here, thus along a streamline. dy over dx is equal to v over u, which is equal to 1.5 minus 0.8y divided by the sum 0.5 plus 0.8x. We solve this differential equation by separation of variables. dy divided by the difference 1.5 minus 0.8y is equal to dx divided by the difference 0.5 plus 0.8x, which leads to the integral of both sides of the equation, and after some algebra, we solve for y as a function of x along a streamline. Y is equal to c divided by 0.8 times the sum of 0.5 plus 0.8x, all plus 1.875, where c is a constant of integration that can be set to various values in order to plot the streamlines. Several streamlines of the given flow field are shown in figure 4-17. Discussion. The velocity vectors of figure 4-4 are superimposed on the streamlines of figure 4-17. The agreement is excellent in the sense that the velocity vectors point everywhere tangent to the streamlines. Note that the speed cannot be directly determined from the streamlines alone. Figure 4-17. Streamlines, solid black curves, for the velocity field of example 4-4. Velocity vectors of figure 4-4, blue arrows, are superimposed for comparison. A stream tube consists of a bundle of streamlines, figure 4-18. A stream tube consists of a bundle of individual streamlines, much like a communications cable consists of a bundle of fiber optic cables. Since a streamline by definition, streamlines are everywhere parallel to local velocity, fluid cannot cross a streamline by definition. By extension, fluid within a stream tube must remain there and cannot cross the boundary of the stream tube. You must keep in mind that both streamlines and stream tubes are instantaneous quantities defined at a particular instant in time according to the velocity field at that instant. In an unsteady flow, the streamline pattern may change significantly with time. Nevertheless, at any instant in time, the mass flow rate passing through any cross-sectional slice of a given stream tube must remain the same. For example, in a converging portion of an incompressible flow field, the diameter of the stream tube must decrease as the velocity increases in order to conserve mass, figure 4-19a. Likewise, the stream tube diameter increases in diverging portions of an incompressible flow, figure 4-19b. Figure 4-19. An incompressible flow field, a stream tube, decreases in diameter as flow accelerates or converges, and increases in diameter as flow decelerates or diverges.